To model the dependencies among the prices of different assets in the Black-Scholes model, we will assume that the joint distribution of their log returns is a multivariate Gaussian. Consider a d-dimensional random vector x that follows a multivariate Gaussian of parameters mu and sigma. Mu is a d-dimensional vector of means, and sigma is a d by d covariance matrix. The PDF for this random variable is a function of x, a d-dimensional vector in R to the d, and parametrically of mu and sigma. It is equal to a normalization constant 1 over 2 pi to the d halves times the determinant of the covariance matrix to the 1/2 times the exponential of minus 1/2 x minus mu transpose times the inverse of the covariance matrix times x minus mu. The vector of means, mu, is the expected value of the random vector x, and this can be computed with this numerical quadrature. Sigma, the covariance matrix, is simply the expected value of x minus mu times x minus mu transpose. The diagonal elements of this covariance matrix are simply the variances of the components of the random vector x. The off-diagonal elements are the covariances between the components I and j of the random vector, where I and j are indexes that run from 1 up to capital D, the components of the random vector. From the elements of the covariance matrix, we can define the correlation matrix. The ijth element of the correlation matrix is simply the covariance between the I and j components over the geometric mean of the variances for each of the components. Notice that the diagonal elements of the correlation matrix are equal to 1 and that the off-diagonal elements are smaller or equal to 1 in absolute value. Let's look at the PDF of a two-dimensional Gaussian in more detail. On the left figure, we can see a three-dimensional plot of the PDF of the bivariate Gaussian. This dimension corresponds to one of the components, this other dimension to the other component. The value plotted along the vertical dimension corresponds to the height of the PDF. Notice that the Gaussian has a maximum at the point that corresponds to the means of each of the components, in this case 1 and 3 respectively. On the right-hand side, the Gaussian is seen from above. It is the contour plot of the two-dimensional Gaussian. These curves are contour curves. They link points at which the PDF has the same value. Blue corresponds to lower values of the PDF. Red corresponds to higher values. The contour curves are ellipses centered at the point that corresponds to the mean of the Gaussian distribution. The axes of these ellipses correspond to the eigenvector of the matrix of covariances.